Welcome to my channel AI Basics with AK. Here we are with another new episode on season 3 Introduction to Statistics, episode 7 Hypothesis Testing. In our previous 3 episodes, we covered the most important basics of machine learning, which is episode 7 Center Limit Theorem, episode 8 the confidence intervals, and episode 9 the t distribution. And now let's step back. What could it answer in terms of uncertainties? Ideally, we do not know about the population distribution, right? So the central limit theorem gives us comfort that if you have sufficient samples, the distribution of population mean becomes normal. This is a very good approximation because be it be any population, if we have sufficient samples, we can use normal distribution. Simple. Now, with how much confidence you can guess that this could be the population means, that's where the episode 8 comes into the picture that, okay, given you want 80% confidence or 90% confidence or 99% confidence, this could be the possible range of the population mean. Now, that's what we have learned in our episode 8. In our episode 9, we have further loosened some of the constraints that, okay, what happens if you don't have sufficient sample? That's where the t distribution comes into the space, because it could even tells that, okay, because the tails gets heavier, because we are accounting to that uncertainty, because we do not have sufficient sample, and your possible ranges of values could increase, which is accounted by the introduction of a concept called degrees of freedom. Now, and also we have seen that as the sample size increases, the t distribution tends to become a normal distribution. Beautiful, right? On one side we have a comfort, okay, but be it be any population, we could use normal distribution. And also on the other side, if we don't have any, if you have very less sample size, okay, still you could use a t distribution. This is a very important approximations that laid the fundamentals of machine learning and as well as inferential statistics. Let's extend these fundamentals into one more fundamental topic, which is especially applicable in most used concept of A/B testing. Now let's jump into our today's episode topic, which is hypothesis testing. Let's start our episode 10 with a simple story. A company claims that their new drug reduces blood pressure. How did they claim it? They tested it on 40 patients and the average blood pressure did drop. Well, from our previous three episodes, if we step back and observe it, we can say that, okay, can we claim it? Might not be, because once a drug is claimed that it worked, we introduced to the population. We do not know about the distribution of population. So we have to infer what could be the drop in average blood pressure for the population, right? That's where we cannot rely on a single matrix of average, but we have to rely on the range kind of a thing. But that's very problematic, right? Like we cannot say that, okay, the average blood pressure could be of this range, because it's a policy decision. Do we want to introduce it as or a no? That's where the hypothesis testing solves that problem of a decision making, rather than telling that you give a range of possible values and then you tell somebody, to a decision maker, you decide, okay, this could be the population range of values. Exactly, we use these maths that we have learned previously to solve the decision making pieces by using hypothesis testing. And this is exactly the backbone of all the decisions that taken places in medical trials, A/B testing, quality control, as well as in policy decisions. Beautiful, right? Now let's understand what is hypothesis testing. By all means, there are two hypotheses. There is something called null hypothesis and there is something called alternative hypothesis. Null hypothesis says that nothing has happened. There is no difference. Okay, nothing has happened. Okay, it means we have introduced the drug, we have tested on 40 samples, and The null hypothesis says that, okay, the drug has no effect, kind of a thing. Now, the alternative hypothesis is that the drug has effect. It's like a simple yes or a no, right? Okay, no, let's not introduce the drug. Yes, let's introduce the drug. It's a very simple for a policy decision when you have a no or an yes kind of a pieces rather than giving a range of possible values. So the now let's step into further building it out. Okay, see, okay, what kind of real world examples or decision making it could solve it. Now let's introduce a direct trail. Let's introduce it. Okay, the null hypothesis answers no, and alternative hypothesis gives let's introduce it. I made some changes to the website. Whether can I deploy version B into the real directly onto the production server? The null hypothesis says no, and the alternative hypothesis gives a decision that you can, yes, you can deploy it. Similarly, the coin fairness and also in manufacturing. Say, for example, you want to arrive at whether the machine should be replaced or it has to be repaired, or it can be anything. So the machine produces 500 grams on an average, which is good. So it doesn't needs to be replaced. Yes, maybe here the machine is off, so maybe it needs some maintenance or it has to be replaced. So always observe that the null hypothesis is always that we choose not to take any action. Here, if you could see on here on all these things, we choose not to take any action. The drug has no effect. It means we are not taking any action. Version B is not performing very well. It means we are not taking an action to deploy the version B into the production server. Similarly, we are not claiming that the machine has to be replaced. So that's the null hypothesis. It means we are staying with the current status quo. Let's extend this logic such that it just ingrained into your thought process. You know about the court proceedings, right? Like the one of the greatest principle is that innocent until proven guilty. So what happens ideally when the two teams argue is that how does one person proves a guilty is that you bring a strong evidence and you reject that, okay, he is not guilty, he is not innocent, and then you claim that, okay, he is guilty. Or else you stay with the core piece that, okay, we do not have any strong evidence, and you claim him that he is still innocent because you do not have any strong evidence to prove him guilty. These are the two important pieces of decisions we always take. Either we reject a null hypothesis or we fail to reject null hypothesis. Do remember, we are still not claiming that the null hypothesis is true. We are just claiming that either we are rejecting the null hypothesis, it means that we have sufficient evidence to refute and make a decision. Here we are trying to make a decision and go ahead. On the other piece, we are unable to make any decision because we do not have any strong evidence that the null, the whatever the claim that we want to take it for alternative hypothesis is true. So that's where we try to reject the null hypothesis. But here we are not saying we are rejecting alternative hypothesis. Here we are trying to say that we have failed to reject the null hypothesis. These are important pieces that we can always do it, because either we can get more information, we can collect more evidence that maybe down the line, once we have failed to reject null hypothesis, such that we can reject null hypothesis. That's how usually it happens, right? In the courts, they give more hearings such that the both of them have a sufficient chances to either reject null hypothesis or fail to reject null hypothesis. And finally, we can take a decision once we feel that, okay, we have sufficient data, and any collection of sufficient data doesn't make any change in decision in future. So far, we have seen that in the earlier episodes that the population mean, the distribution of population mean would be approximated to the normal distribution. Isn't it so? Okay, let's forget about T distribution and at this point of time. Now, the population mean cannot be a single value, but it can, the values can range depending upon our confidence. Now, let's overlay this with respect to our hypothesis testing. What does hypothesis testing says? The H naught, okay, is nothing but your null hypothesis, and H alternative is your alternative hypothesis. And also, we have seen that the null hypothesis is our default decision making. So what does it mean to put it, to overlay this on statistics is that we assume that whatever we are assuming with respect to null hypothesis, this data is our population data. And so that's why we see that this distribution, say for example here, okay, this is my normal distribution. Now assume that we have collected sample data, but however, the mean of the population is coming here or here. It's not coming in between here, which is usually should be the possible range of values if my null hypothesis is true. But based on my new evidence, the population mean might be here or might be here. So what we say here, we reject this null hypothesis based on the information that we have it, that the evidence, because the population mean could be in these extremes. That's the basis. So that's the understanding I'm trying to give here in the p-values. P-value is nothing but my probability. The probability of lying here on these extremes is what we are trying to calculate it. Now, when do we reject it? Here still we arrive at, say for example, probability can be 0.1, 0.05, 0.5 kind of a thing. So usually we reject it, okay, whenever the p-value is less than alpha. Usually alpha is 0.05. It means the probability, we are giving 95% confidence or chances the null hypothesis to be true, and then only with the sufficient sample we have it, we can refute or reject the null hypothesis, because we are no longer establish a credible evidence that the population mean could fall under these possible ranges of the null hypothesis. But one can question back, okay, why are giving 95% confidence to prove, okay, automatically for the null hypothesis? Why can't it be 50%? Let's step back, okay, into our definition of null hypothesis. We are not saying we are agreeing the null hypothesis. We are saying that we need a sufficient evidence to reject the null hypothesis. So that's the reason we are giving and the null hypothesis under normal scenarios, if we want to be 95% confidence this is the null hypothesis, we need more confidence to reject the null hypothesis. That's the reason we commonly choose alpha is equal to 0.05. Okay. Having this intuition understanding, let's jump into the next slide. Okay, I think let me refresh this slide. Now you can see that if my probability, okay, here is 0.23. That's the reason you can see that we cannot reject the null hypothesis. And as I change it, okay, I can see that, okay, it falls in here, okay. And as I change further here, you can see here, okay, the distribution is less than 0.05, alpha is less than 0.05, so we can reject the null hypothesis, and because we have a stronger evidence to reject it. Got it? As we have, there is a moderate evidence, it means the p-value, we do not have any sufficient evidence to reject null hypothesis. We have moderate evidence, and then we have a stronger evidence. It all depends upon what is your threshold of your acceptance. This is a common threshold. Alpha is equal to 0.05 is a very common threshold value. So let's go back through the 5-step framework of hypothesis testing. First, usually we define H0 and H1, which is what we have seen it here. Like drug has no effect or drug has an effect to reduce the blood pressure. That's the fundamental decision we take it in the step 1. The step 2 is that choosing that significance level. How surprised must I be? Usually it is 0.05. Compute the test statistics. Either G-score or T-score is fine. Okay. And don't worry about calculating all these things. In the next couple of, I think in the next episode, in the 12th episode, I'll be running all of these last few episodes just with couple of Python queries. Like two lines of Python code is sufficient for last 5-6 episodes. But having a conceptual understanding is much more important. And the step 3 is computing that score, and step 4 is finding the p-value, and step 5 is taking a decision. In a 2-step process, it's just very simple, but we are laying a 5-step process is because you decide what decision needs to be made and what is the threshold of a decision, and you compute the statistics and the values, and then finally you take a decision. One-tail test and a two-tail test is very simple, is nothing but here the H0, as I said it out, is a 500 grams kind of a thing, and alternative hypothesis is it's over or under, okay. It means we are taking a decision. But however, we don't need to worry if it is the machine is producing less than 500, but only if it is producing more than 500 grams, it means we need to change that machine or correct that machine. So whenever there is only one side kind of a thing, like less than 500 or greater than 500, usually we take that decision as a one-tail test. What is it? Two-tail test or one-tail test kind of a thing. To put it simple, we have seen this normal distribution, right? Two-tail means, okay, the p-value can fall here or here. One-tail means, okay, either it is here or it is here. Got it? So that's the reason. It's here, you could see here, it is a left rejection zone and a right rejection zone. Got it? And if it is in greater than 0, it means it is a right rejection zone. Simple. Now let's jump into our next slide. Here you could see that this is an two-tail test where we have probability of 0.5. It means, okay, let me go through the setup first. Like we have a suspected coin is biased. So we have to arrive at a decision whether whenever we toss it, okay, is it fair or not? It means the probability is 0.5 or not. If it is not 0.5, we can assume that the coin is biased. So for that, we have calculated a sample by tossing that coin 100 times and we got 62 heads. So step 2, we have arrived at an alpha that the decision threshold is 0.05. We computed the G-score. G-score we got as 2.4. From the G-score, we calculated the probability wherein we have arrived at as 0.16. So 0.16 is of course less than 0.05. So we reject the null hypothesis and we deduce that the evidence suggests that the coin is biased. Don't worry about all this, Max. Right now in Python, it's a two-step, two-line code, so don't worry about it, all these things. But just I'm giving you an conceptual understanding how we can do a hypothesis testing. So here you can see that 45 heads out of 100, the z value is in between here, okay, but my threshold falls on the extreme left hand side on the shaded area, so we are unable to reject it. But as I increase it, still I am unable to reject it. But as I got 62 heads, I am able to reject it. And 70 heads, I'm still able to reject it because I can't see the red mark here, but it's actually under the blue line. But you can see that, okay, when it is 45 heads, there is no need to reject the null hypothesis, because 45 heads out of 100, it means, okay, it's sufficiently fair coin. 52 heads, it's perfectly fair coin. That's why you see the z value exactly at the center point. But 62 heads might be a biased. Of course, 70 heads, most of the time it's the biased one. Beautiful, right? So, yep. So far in this episode, we have recapped the basic understanding of central limit theorem, confidence intervals, and the t-distribution things into a hypothesis testing, where we are applying the learned statistics into a decision-making pieces. Beautiful, right? Now, for the first time in this season 3, I am giving a homework for all of you. So there are a couple of two simple questions, okay? Just do this simple questions, and then you can update it in a Jupyter notebook file or a Python file, or even, okay, you can update as a notebook file and then share that piece in your comments here, okay, if it is needed. But yeah, this is very basic, simple. Even if you just give this question into any GPT right now, it gives you the answer. But yeah, it is more for your learning and understanding the basics. Thanks a lot. See you in the next episode, and have a lovely day.